Hi guys, welcome back. So another data analysis video. In this video I'm still looking at how to conduct ANOVA using the different software packages in Python. And prior to this video I made a video demonstrating how to conduct different assumption checks that you might need to conduct when you're fitting some sort of ANOVA model. So checking that the data is normally distributed and you have homogeneous variance or sphericity. Prior to that, I created a couple of videos where I demonstrated how to conduct a one-way repeat measures ANOVA, and I think we used the SciPy stats library to conduct that. In this video, what I'm going to do is another example of a one-way repeated measures ANOVA. This time what we'll find is we'll get a significant ANOVA result, so I'll follow that up with post-hoc tests. Okay, so there are a number of Python software libraries we could use to run this analysis, but in this example what I'll use is the pingouin library's RM underscore ANOVA method. And it produces really nice output. It gives us a lot of useful information for interpreting the analysis. And then I'll also use the pingouin pairwise test method to conduct post hoc tests once we get a significant result. Okay, so to start with, I'm going to import pandas, numpy, and pingouin. So I'm importing pandas as PD, numpy as NP, and pingouin as PG. As is common, as is kind of conventional, using those nicknames essentially. Right, so in this video I'm going to use the EDA polygraph data set that I've kind of used to demonstrate these analyses in previous videos. So this is data from a lie detector study with it's got a repeated measures independent variable called questions, and that variable has three levels: whether the participant lied, told the truth, or completed a control task in response to each question that was asked. So the dependent variable was the participant's mean arousal, and that was recorded using electrodermal activity, so their skin conductance essentially, when they told a lie, said the truth, or they complete this kind of neutral task where they just looked at a piece of paper with a coloured shape on it. Okay, so I'm going to import the data set. I've got it saved as a CSV, and this is data. This is kind of data that was collected by a couple of my colleagues, and we've kind of used it multiple times for undergraduate coursework and things like that. So I'm going to import it and save it as an object, a data frame object, called EDA underscore DF, so EDA data frame, and I'm using the PD, the pandas.read underscore CSV method, and just passing the name of that particular data set, what I've got saved on my computer as a string. So it's let's call a head. We'll use the .head method to look at the first 5 lines of data, and you can see there are a couple of variables. There's a person ID variable which contains the identification number of each participant. There's a variable called framing. We're going to ignore that in this video. We're not going to look at that because we're just doing a one-way design. We've got this questions variable. Remember, that's the IV. It's got 3 levels: lie, truth, control, colored squares, task. And then we've got arousal, and this is our kind of DV, the measure of EDA arousal when they were lying, telling the truth, or doing the control task. Okay, so I'm going to conduct this repeat measures ANOVA using the pingouin RM underscore ANOVA method. So previously I think I used the SciPy repeat measures ANOVA RM method. This is slightly different, and it gives us quite quite detailed output, which is good. And the parameters we have to pass to this method are the data, the DV, the within subjects factor, some sort of subject participant ID to account for the fact that we have structure in the data coming from multiple data points from the same participants. And then there's this kind of additional parameter that I've included, detailed equals true, which means it will return the result as a nice kind of HTML pandas data frame, so it looks nice. So I'm going to create an object called res for results, essentially the model results, and I'm going to set that equal to PG, so pingouin.rm underscore ANOVA. So that's the syntax to use this method. And then I'm going to pass all those parameters that I just said we needed. So data is going to be our EDA data frame. The DV is our arousal variable. So that's going in as a string with single quotes around it. Within is our within subjects factor or the repeated measures factor, and that's this questions. So I've got they're going in obviously typed exactly as they're saved in the data frame. So it's this questions underscore LT col. That just basically questions, lie, truth, colored squares. They were saved to that just because it was convenient to remember what they're related to. Subject equals person ID. So that's we're having to pass the identification number of each participant to account for the fact that it's repeated measures design, and then detailed equals true. And if I run this cell, if we actually call the results object, run that cell, you can see we get this nice data frame here. We actually get this nice table where it shows us, it gives us the sum of squares, the degrees of freedom, the mean square, our f value. It gives us an uncorrected p-value and a corrected p-value, which is really useful, as you'll see in a second. We're going to ignore NV2 and EPS for now. It also includes, without us actually having run this separately, it includes a test of sphericity, so Mauchly's test of sphericity, to see if our data meets the assumption of sphericity, which is, as I said in the previous video, is similar to an independent group's assumption of homogeneity of variance. Okay, so you can see here we've got sphericity. It gives us the omega value W hyphen sphere for sphericity and the p-value for the sphericity test. And it's telling us, it returns a nice Boolean value, tells us whether it's true or false that we can assume sphericity in this data set. It's telling us it's false. Gives us an omega value of 0.92 if we round that, and a p-value of 0.03 or 0.035, let's say. Okay, so we've got a significant Mauchly's test of sphericity. So what that means is we've violated the assumption of sphericity, so we can't assume sphericity. So in this case, we're going to need a more robust test of significance. So to ensure that we're not kind of reporting erroneous results. And as I mentioned previously, in the output, Pingouin has provided us with a p-value that's been corrected for violations of sphericity using the greenhouse geyser method, and that's this P-GG-core. So it stands for P greenhouse geyser corrected. Okay, so we could use this adjusted p-value that we see here to adjust the analysis to allow for the fact that we can't assume sphericity between the groups in the data. Okay, and if we're using that, you can still see we report the same p-value, 14.22 it would be if we round that to 2 decimal places. But even using the corrected p-value, we can still see we've got significant f value there. We've got significant results. So p is less than 0.01. It's actually 0.00004, something like that. Okay, so if we're reporting these results, we might put something like I have here in this markdown text. So we'd report greenhouse geyser corrected ANOVA produced significant results. We have F with open parentheses, which report the between subjects degrees of freedom and the within subjects degrees of freedom. So 2 and 158. Hope it's clear where they came from. Report equals, and then report the F value, 14.22, comma, P is less than 0.001 if we use the greenhouse geyser correction. Okay, so we've got a significant ANOVA result for this repeated measures model. I think this is the same repeated measures analysis that I conducted in a previous video, but I didn't then follow it with post-hoc tests. So now we know there's a significant difference between at least 2 of the levels of our independent variable in terms of mean arousal. But what we now need to do is kind of look at all pairwise comparisons of the levels of the independent variable. We've got 3 lie, truth, colored squares, to see which ones are significantly different from each other. So we want to perform post-hoc comparisons on all pairs of conditions of the IV, the independent variable questions. And we can do this using Penguin's pairwise tests method. So pairwise underscore tests method is what we'll use. And I'm going to use a Bonferroni correction. So remember, when we are conducting pairwise comparisons like this, we're inflating the possibility of making a type 1 error. So we're increasing the probability that we will report a significant result when there isn't one. So we need to adjust the p-value that we would accept as significant based on the fact that we're doing multiple tests. We're conducting multiple tests. Okay, so I'm going to use a Bonferroni correction for this. And to do that, to calculate that manually, I've demonstrated this in another video. All you do is you take your kind of standard p-value, whatever it is that you might be using in your discipline. You know, in psychology, it's usually 0.05. You divide it by the number of comparisons, the number of tests you're conducting, so pairwise tests. So in this case, we've got three levels, so we'll be conducting 3 comparisons. Lie with truth, lie with colored squares, truth with colored squares. Okay, so to the syntax for this post-hoc test is I'm creating an object called post_results, just so it's easy to call. Set that equal to PG, so penguin.pairwise_tests. That's the method we're using, and hopefully you can see, hopefully it's clear here, the different parameters we're going to put in, the different arguments. So I'm specifying the data. We want our EDA data frame. The DV is still arousal. Within subject's factors are the questions. Subject is our person ID. I'm specifying parametric equals true. So we're conducting parametric tests. And p adjust equals, you can see here in this string, bonf in single quotes. So this is, I'm basically telling it to use a Bonferroni, bonf is short for Bonferroni, a Bonferroni p adjustment. There are others you can use, you can specify them, and if you look at the Penguin documentation, it'll tell you which ones you can use. I'm just going to use Bonferroni here. It's quite a common use one. I don't see an issue with using it in most cases. Quite strict adjustment of the p value or the threshold of significance. So f size is effect size, and I'm asking for Hedges effect size here. So Hedges G, and that will give us some interesting results as well. We'll have a look at that shortly. So I'm just going to call that object that we've specified the syntax for this model, and what you can see here is you can see the comparisons. It's showing you which ones it's contrasting A with B. So it's level 1 with level 2, level 1 with level 3, level 2 with level 3. So 1 is lie, 2 is truth, 3 is colored squares. I know that because I know what the data looks like. So this first line here is comparing lie with truth, and it's given us a t-value, telling us the degrees of freedom. It's given us an uncorrected p-value. So this would be if we just conducted a t-test without making any adjustments, such as Bonferroni, of the threshold, the p-value. It gives us a corrected p-value, which is obviously our p-value after, whilst using a Bonferroni correction, and it tells us the adjustment method as bonf here. Hedges is given at the end, and that's our effect size. I'll talk more about that in a second when we talk about what the results mean. Okay, so the next line, this next row, we're comparing lie with the control colored squares condition. We've got a t-value of 4.48. Our corrected p-value is less than 0.01. So the one previously, when we looked at lie compared to truth, we had a t-value of 1.13 if we round that to 2, but the correct p-value is 0.79, so not a significant difference between those two levels or conditions of the independent variable, but there is between lie and the control condition, and 2 is truth, 3 is the control condition. So comparing truth and control, we get a t-value of 4.10 if we round that up to 2 decimal places, and a corrected p-value of 0.0003. So again, significantly different. So what we're seeing here is we've got a significant difference between lie and the control condition and between truth and the control condition, but not a significant difference in arousal between those lying and those telling the truth. Okay, given this was a lie detector test, that's kind of not a great result, really. Okay, but knowing that they are significantly different is only kind of part of the picture, really. So we know that lie and coloured squares are different and truth and coloured squares are different, but it'd be useful to have some descriptives to be able to interpret the direction of these significant comparisons. So which had the highest arousal? Was it lie or was it the control condition? We don't know that just by looking at this, we can't assume that. So what would be useful is just to obtain some descriptive statistics to help us interpret the direction of the effects or the differences we're seeing here. So to do that, all I'm going to do is create some labels, some labels for the questions variable, obtain some descriptive statistics for mean arousals for the three different groups separately. So what we want is a mean arousal score for lie and a mean arousal score for truth and a mean arousal score for coloured squares. And I'm going to do that. I've kind of demonstrated this previously, how to sort of use the map function and create new objects essentially that sort of like consolidate the information you want. So firstly, I'm going to use the map function to add labels to the questions variables. So I'm going to just map lie to 1, truth to 2, coloured squares to 3, and append that as quest_cat, so questions categorical. So a new variable, I'm just appending that to the data frame so we can see. Gives it more meaningful labels, helps us interpret things. So then I'm going to create a couple of new objects for the IV and the DV. So the IV here is going to be our questions category variable, and the DV I'm going to create is our mean arousal. And I'm going to create objects. One's called cat and one's called scale. So it gives us an indication of what they are. Obviously, the DV is a scale variable. The IV is a categorical variable. Those are just the names I've given them, so it makes it easier to understand what I'm doing here. And then we're going to create 3 Boolean objects where we're going to split category up by level. So we're going to split cat. We've now got this object called cat. We're going to split it up into three more objects, which basically extracts each group from the cat object. So cat 1 is going to be lie, cat 2 is going to be truth, cat 3 is going to be coloured squares. Okay. And then we're going to sort of stitch these things together, really. We're going to extract the scale values just for cat 1 and then for cat 2 and save them as cat lie arousal, cat truth arousal as 3 different objects. Right, having done that, that's kind of a little bit, if you kind of know how to do that, it's quite straightforward. But once we've done that, what we can do is basically just get the mean of each of these objects, and that will give us, so this first one will give us the mean of mean arousal in the lie condition, mean arousal in the truth condition, mean arousal in the coloured squares condition. And I'm just going to format them nicely so we can see what they mean. So I'm using a print statement, I'm using an F string, this F, and then we're using these double quotes here. I'm going to specify mean lie arousal, and then in the brackets there, we're just going to take one of these objects, use dot mean, and I'm asking for it to be rounded to 2 decimal places with this little bit of syntax here, .2f. Okay, same with the others, and if I run that, the output will make it clear what I've done there. So what we can see here is, we know we've got a significant difference between some of our groups. We can see that the mean arousal in the lie condition was 2.09, in the truth condition it's 1.88, and in the control condition it's 1.05. So we can see which had the higher and which had the lower means. And we know that lie, so 2.09, was significantly higher than control, 1.05, and we know that truth, 1.88, was significantly higher than control, 1.05. We also know that lie, the mean of 2.09, although it is higher than truth mean of 1.88, it wasn't statistically significantly higher. So there's no statistically significant difference between those. So to summarize, let's summarize these results all together from this analysis. So I've added labels to them, we've got some descriptives, it helps with interpreting it. And what we can see from this particular data set is that with the lie condition with a mean of 2.09 and the truth condition with a mean of 1.8 are not significantly different. You can see that from the t-test above. So t brackets 79, so we obviously need the degrees of freedom. Let's go back up, we can see that. So we can see the degrees of freedom are there. We're going to use our corrected p-value, Bonferroni corrected, 0.79. And then I've not mentioned it yet, but I did say it was there. We asked for Hedges G, and that represents a small effect size. G equals 0.09. So what represents a small, medium, or large effect size? You have these kind of canned type of cutoff points. If you Google them, look them up online, it'll give you an indication. If you get an effect size this big, it's a small effect size. If it's this big, it's a medium effect size. They're not great, but they're just kind of a kind of rough and dirty rule of thumb to give you an idea of how large the size of the effect is. So for this first comparison where it wasn't statistically significant, we didn't get a significant t-test comparing the lie to truth, we can see that it represented a small effect size. Our Hedges G is 0.09. For the lie and control cut squares comparison, we did get a significant difference. We got a t-value there of 4.48 and p is less than 0.001. This represented a medium effect size using Hedges G. So Hedges G was equal to 0.52. You can see that there. That was the last column of R. There we go. If we round it to 2. Yep. And finally, we also got a significant difference between the truth and coloured squares. So our t-test, t brackets degrees of freedom 79 equals 4.10. P is less than 0.001. So that represented, in this case, a kind of small to medium effect size with a Hedges G equal to 0.40. So like I said, you can, if you Google Hedges G, it'll sort of kind of give you an indication of what's considered a small, medium, and large effect. I think that's it for this particular video. So what I've done here is we've used the Pingouin RM ANOVA method to run a repeat measures one-way ANOVA. It's given us some nice output. We found that we've violated the assumption of sphericity, so we've used the corrected greenhouse Geyser corrected F value, and we've found that was a significant result, and then we've conducted pairwise t-test comparisons using a Bonferroni adjustment, and we did that using the Penguin pairwise _tests method. And that showed us that there were significant differences between the lie and control condition and the truth and control condition. Okay, hopefully that was useful. So it's some indication of how to do the analysis and how to interpret and report the results. Thanks for listening.